Have you ever wondered how big the universe is? How many stars are there? Does space go on forever? The answer depends on the shape of space. Let's explore some possibilities. There's an interesting star. This star looks familiar. Haven't we been here before? What's going on? What kind of space is this where we keep seeing the same stars again and again? It's easier to explain in a two-dimensional universe than a 3D one. But what would a 2D universe be like? Let's call it flatland. Life in 2 dimensions has its problems. When 2 flatlanders want to pass one another, they can't go around each other or to the side as we would, since they can't leave the plane. Our athletic flatlanders must jump over one another to continue on their way. The flatlanders live on the one-dimensional surface of their 2-dimensional planet, just as we spacelanders live on the 2D surface of our 3D planet. The flatlanders' planet is orbiting a sun. Their sun is a 2-dimensional disk, just as our sun is a 3-dimensional ball. Like ours, their sun is just one of many stars in their universe. Let's watch the flatlanders explore their universe. They head straight off into space and are surprised to come across their own sun. Perhaps their universe is a sphere and they took a trip around its equator. Or perhaps it's a cylinder. Or a torus. Each of these surfaces is a possible shape for a 2-dimensional universe. Note that we have taken advantage of our 3-dimensional space to see something that 2-dimensional flatlanders can't see directly. In a similar way, 4-dimensional people could draw 3-dimensional universes in their space, but that's another video. We 3-dimensional people can see them without the 4th dimension. We can visualize 3D spaces using only 3 dimensions for our drawings. We first try to understand a flatlander's universe without the extra dimension. Suppose their universe is a torus. We'll save a copy of it, cut the torus once, and deform it into a cylinder. Cut it again, and open it into a square. This square is a fundamental domain for the flatlander's universe. We now see their universe using only 2 dimensions. The flatlanders can still travel about their universe as before. When looking at a fundamental domain, we must imagine that its edges are glued together. Anything leaving one glued edge returns at the other. The way we glue them determines the shape of the space. It doesn't matter where we put the cuts. We need cuts to draw the fundamental domain, but they don't really exist in the space itself. When our cut passes through the flatlanders, they don't feel a thing. What do the flatlanders see in this universe? Their line of sight travels around the universe, and they see the back of their own spaceship. Like the flatlanders themselves, their line of sight can't leave their 2-dimensional space. They see what appears to be a copy of themselves. Indeed, they see images of themselves in many directions. This tiled picture shows what the flatlanders see and that their universe is boundless. They'll never reach an edge. From the picture of the single fundamental domain, we see that their universe is not infinitely large. It contains only 3 stars and 1 spaceship. It's finite. Neither picture alone gives the full story. By combining these 2 pictures in your mind, you can get a better understanding of the true nature of their space. Now we're ready for 3 dimensions. Take a cubical block of space. We'll use this for our fundamental domain in 3 dimensions, just as we used a square in 2D. We glue the left and right walls. Now the spaceship can travel around this finite universe, passing the same stars again and again. We glue the top and bottom. And finally glue the back to the front. Now the space has no boundary and the ship can travel in any direction. This space is called a 3 torus. Let's ride the spaceship inside the 3 torus. Even though the 3 torus is finite, we have the illusion of flying in an infinite space. There are only 2 stars in this universe, but we see each one over and over. This isn't the only possible shape for space. Before we visit another 3D universe, we'll look at the corresponding 2-dimensional space. Its fundamental domain is again a square. This time we glue the left and right sides with a flip. This surface is called a Möbius strip. When the spaceship takes a trip around, it comes back upside down. The flip makes a difference in the shape of space. A second trip restores it to its original condition. Let's watch the trip again on the original square. Now glue the top and bottom of the square with no flip. What do the Flatlanders see in this space? Looking up, they see the bottom of their own spaceship. Looking forward, they don't see their ship right in front of themselves because of the flip. Their line of sight keeps going across the bottom. When it wraps around a second time, it's flipped again, and they finally see the back of their own ship. The Flatlanders have the illusion of seeing a reverse copy of their universe, followed by a regular one. They see infinitely many images of their universe, half reversed and half not. What if we do this in 3D? 2 pairs of faces connect as in the 3 torus. To make the flip, connect the top of the right face to the bottom of the left face and vice versa. After 1 trip, the spaceship appears mirror reversed. After a second trip, it returns to its original state. Let's see what this space looks like from the inside. As in 2D, we see infinitely many images of our ship. Half are mirror reversed, half are not. When we roll, our reversed images roll in the opposite direction. Life in this space is different than in the 3 torus, where all the copies of the ship move in the same direction, like a flock of birds. We fly this way and see ships in neighboring rows flying in the opposite direction. The mirrored images turn as we do, to fly along paths that seem to cross ours, but they can never hit us. That's impossible in this space. We've looked at only a few of the many possible shapes for space. There are other ways to glue the walls of a cube together. Or instead of a cube, we could use a different shape for the fundamental domain. The space we saw at the beginning of this video was really a 3 torus containing only 96 stars. This space is finite, but boundless. Astronomers face similar possibilities as they try to understand the real universe we live in, whose shape is still unknown. It is much larger than the simple spaces we've seen in the video and contains vast numbers of stars. But the same principle applies. What seems to be a star in a distant galaxy could be our own sun. The light we receive from it could be light which left the sun billions of years ago, traveled around the universe and is just now completing its trip. If we can someday find a pattern in the arrangement of the galaxies, then we will know the true shape of space.
Look at those beautiful tulips!
All right. Neat. You have a nice garden here. We're born into the world. Everything's a surprise to us. We go out, we want to see what's there. And asking about the shape of space is just asking about this largest scale, saying what's the playground that we find ourselves in here? What's the shape of the whole thing? That was special.
In the physical universe, curved space is a possibility. But in the mathematical universe, it is very much a reality. And Jeff Weeks has devoted his life to exploring it.
Even though this quest for understanding the shape of space is a relatively new question, it's part of an intellectual tradition that goes back thousands of years to the Greeks. Our mathematics is, in a sense, spacemetry instead of geometry. Rather than just measuring the Earth, we're now going and measuring space. We're trying to develop mathematical models that explain what we see when we look into space.
Like a biologist classifying new species, Weeks is cataloging the shapes of three-dimensional space. Each is a model astronomers can use to test their observations. Among thousands in his library, one may someday be found to be the shape of our universe.
I've written the computer programs to increase what we know about the mathematical universe. So it's like this big world filled with these creatures. I mean, not physical creatures, but mathematical creatures. And we want to learn something about them. We want to learn how they're related to one another, what the patterns are. There are these beautiful interconnections, and we just don't understand all the details.
Curved spaces have properties that are similar to the Earth's surface. A person going in one direction will eventually return to the starting point. Although the Earth's surface is a finite area, someone can travel forever in any direction without ever reaching an edge. The same can be true of curved space.
It's going on its way. The central mystery is how you could travel off in one direction and come back from the opposite direction. In 2 dimensions, this is easy enough to understand. Think about the 2-dimensional universe, an ant's universe, as it were. If one of these creatures starts off in some direction, they'd imagine they just keep going forever. What else could possibly happen? But there are other possible shapes their universe could have. It could be a cylinder, like the trunk of a tree. Okay, so if an ant starts walking and what it perceives is a straight line around the trunk of this tree, it'll come back to its starting point. Yeah, pretty strange, huh? It's harder to visualize how 3-dimensional people in a 3-dimensional universe could head off into one direction, travel straight the whole time, and still come back to their starting point.
To help people imagine a ride in curved space, Weeks and his colleagues created a video that depicts a bizarre journey.
we're starting with a solid cube of space. We want to think of opposite walls of this cube as being glued to each other so that any creature moving out one wall will come back from the other wall. Similarly, going to the top and the bottom, the front and the back. So this hooks this cube up into a space which has only a finite volume, but it has no edges. You can travel wherever you want, as long as you want. You'll never hit any edge, but there's still only a finite volume to this space.
From the spaceship's point of view, the tiny universe repeats itself endlessly with no perceivable edge or boundary, much like what the earthbound ant would see going around and around the tree. The cube is a simple case, but in all cases, curved space is connected to itself, which implies that if our universe is curved, it has no edges.
The central idea here, the exciting idea is that space could connect up with itself. Faces with the same color are connected to one another so that a spaceship traveling out one face would come back in another face with the same color. So it's like tab A goes in slot B. That's sort of instructions for assembling your space. Okay, let me turn off SnapP here.
Through computer games, Weeks shares his knowledge of curved space with his son.
The reason for writing a game is to give kids something where they could subliminally absorb what this space is like. You want to go first?
I'm white.
Yeah. My son Adam, even when he was a preschooler, he'd look at some of these games like the Taurus chess, where you'd go off one side and you come back from the other side, and this was absolutely no problem for him. When you're 3 or 4 years old, everything in the world is a surprise. Everything's new and wonderful. And why shouldn't it behave like that?
Does that mean that I've won because all you have is your king?
I think that means you won. I'm also in check here. Yeah, I will concede. Good job. Oh, cool.
That's glass, right?
Yeah, it's not normal grass.
Yeah.
I really like working as a consultant.
Be some wood.
I can do my work in the morning, and when Adam gets home, we have a chance to have a few hours together each day.
Oh, yeah. Take that. Wood. I'll go in.
That's an important thing for me. It's nice being able to do it. I think no matter what he ends up doing for a living or what his interests are in life, seeing some of these beautiful aspects of nature, the real nature outside, and also the beautiful aspects of mathematical nature can only make life richer. There are two domains of exploration here. There's the real universe, which we explore physically with telescopes. And then there's the mathematical universe that we explore with our minds, with using the computer as a tool, with pictures. Real nature is beautiful. If you go out and you look at a flower, or you look off into space, it's a miracle that we have this physical universe to explore. I think it's no less a miracle that we also have this mathematical universe to explore. It's full of beautiful, intricate patterns lying there, waiting to be discovered.
For centuries, we have explored two universes and discovered that one leads us back to the other. We have developed mathematics to explore the Earth and to map and navigate its vast surface. Exploring mathematics we have discovered models that enable us to envision the universe. Our journey of exploration may be a voyage like Magellan's that never seems to end, but may someday bring us back home where we began.